Okay, the last example for this section is propagated. We're going to talk about propagated error. So in this case, we're going to have a company that makes a ball bearing, and we always have human error making something, and even machines can make error. Never perfect, and we're saying that this thing's going to err a little bit. So first of all, propagated error is the difference between the exact value and the actual physical measurement. All right, so even with computers and technology, it's getting closer and closer to perfect, but we can never be absolutely perfect. Something's always we're gonna have error somewhere, human error somewhere. So here we're talking about the radius of a ball bearing is measured to be 0.7 inches. If the measurement is correct to within 0.01 inch, estimate the propagated error in the volume V of the ball bearing, and we're gonna say the obviously the volume of a sphere equals 4/3 pi r cubed. So what they told us, they gave us our radius, and they gave us what our change, essentially our change of x can be, our dr. Okay, so they said our radius can vary by that much. So let's go ahead and we'll use our differentials to approximate this, because we just found out that we can use differentials, and it's fairly darn close to actually doing the actual change of x. So let's use our differentials to approximate this. So let's take the derivative with respect to r. So I'd have dv over dr, which is actually just change of v, okay, equals, we'll have my 4/3 out here. My pi is still going to say I'm going to bring my 30 down, so times 3 and r squared. Then subtract my power by 1 times dr. Okay, so obviously these are going to go away, so I have my change of v, so dv dr equal to 4 pi r squared dr. Okay, and we already, well, we know what our radius is, so let's go ahead and let's plug in for r, and we'll plug in for our dr. So I'm going to have 4 times pi times my radius, which is 0.7 squared, times my dr, which is 0.01. Okay, so when I type this into my calculator, I am going to get a propagated error of 0.06158 inches cubed. Okay, so 0.06 essentially inches cubed, and we can go plus or minus. It could be bigger than that, or it could be smaller than that. I should have had a plus or minus here, because it could differ below 0.1. It can differ, in between a negative 0.1. It could be bigger or smaller. Okay, anywhere, any range. All right. So there's our propagated error, and the last thing I wanted to talk about was relative error. We don't know. I mean, we don't know, is 0.06 a huge change? Well, we don't know. All right. So how we know that is we find our relative error. So we're gonna take our relative error and figure out if that actually was a pretty big change or not. And what that says is dv over v, so it's going to be our differential over our actual. All right, so what our differential was, I believe, was 4 pi r squared dr all over v, which is 4/3 pi r cubed, right? 4/3 pi r cubed. Okay, and we can cancel out here. Out of the pi's disappear. Both of these are gone, and this just becomes a 1. Okay, so I'll have 4 dr divided by 4r over 3. When we divide by fractions, that's why I wrote it like this, to show you we save it, change it, flip it, right? So multiply by 3 over 4r. These 4's will cancel out, and so it looks like we have 3 dr over r. So to find our relative error, we're just going to plug our dr in, which was 3 times 0.01 divided by a radius, which was 0.7, I believe, right? And so when we plug that into our calculator, we're going to get a relative error of plus or minus 0.0429. So plus or minus 0.0429. All right. And the last thing that I was going to show you is the percent error. So, well, After we find the relative error, we can find the percent error, and what we're doing is we're just changing this to a percent. So our percent error, so we can err by 4.29%. So is that a huge change? I don't know, about 5%. So is it a huge error? Maybe quite a bit, about 5%. So that's relative error and propagated error and percent error. And there's our last example right there.